Friends, new office chair. Very exciting. I get to be very tall for the foreseeable future. We're very excited. Today we're going to be talking about matrices. And in particular, we're going to start trying to tie together some of the different aspects of linear algebra that I've been talking about and kind of around for the last, I guess, 2 weeks now. Things like why the Gauss-Jordan algorithm works and what matrices have to do with linear maps and in vector spaces in general. And hopefully we'll, by the end of this section, or maybe the next section, we'll have really put it all together. So first thing we should do is we should talk about what a matrix is. Even though I think probably everyone knows what a matrix is, it's important to give a proper definition for what a matrix is. That definition goes as follows. We let m and n be natural numbers. We say that an m by n matrix is a rectangular array, which we'll call by the letter A when we have no other letter in mind. And actually uses capital letters, so I'm going to use capital letters in turn, but it's oftentimes the case that people use lowercase letters inside the matrix and uppercase for matrices. And you will notice that this thing has, other than my bad handwriting making it impossible to notice, it has m rows and n columns, right? So we have an m by n matrix. And then we will use the letter AJK, or I'll oftentimes write lowercase ajk, the corresponding lowercase letter for the capital letter, to mean the entry in position I comma j. In other words, in the ith row in the jth column. So I know you can't really see too much because a lot of what I've written here is just dot 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 dot. But like this is in the first row and second column. We would call that in the 1, 2 entry, and I wrote A1, 2 there. I might also write lowercase a1, 2 some of the time. Now, what makes these interesting is that these things can be used to represent linear maps. And this is the main definition that I want to present today. Okay, I told you what a matrix is, but here's what the purpose of a matrix is. So suppose that you have some linear map between two vector spaces. Let's say it's in LVW. If V1 through Vn is a basis for V, and W1 through Wm is a basis for W, then we can represent T as follows. We know from past propositions that every T is determined by what it does to a basis. And because this is a basis and because this is a basis, every vector in V can be written in terms of these V's. And then every image vector will be written as some combination A1K W1. Yeah, I better say I have to make sure I get the indexing right. A2K W2 and so on. Some combination, or sorry, that should be an M there. MK WM. Some linear combination of the WI, because the WI are also a basis. The coefficients then give us the entries of a column of a matrix, right? You'll notice this is row 1, column K, row 2, column K, and so on. And so in this way, we can encode everything about how a matrix works, basically just, I'm going to use the phrase at a glance. Let's give an example. Let's consider TXY a linear map from F2 to F3 defined by T of xy equals x plus 3y, 2x plus 5y, 7x plus 9y. Well, what happens when I feed in the first basis vector for F2? In the standard basis, that's 1, 0. So what I get is 1, 2, 7. When I feed in the second basis vector, I get 3, 5, 9. And what this definition tells us is that the matrix corresponding to T has these as its columns. The first column for the first basis vector, 1, 2, 7. The second column for the second basis vector, 3, 5, 9. So this is the matrix corresponding to that linear map. And so it turns out that we can use these matrices to basically study linear maps, that just about everything that we may want to know is present in matrices if we know where to look to find everything. For our purposes, just for right now, I'm going to start by proving something which will be useful to us kind of for later. This is that LVW is a vector space. Actually, am I even really proving this? I don't really think so, because I think we kind of know this already. Why? Well, linear maps can be added, right? We have T plus, I don't know, U of X is equal to T of X plus U of X. And of course, CT of X is the same thing as, well, C of TX, or it could even be T of CX. It makes no difference. All of these things are the same. So we know how to add and scalar multiply linear maps. We can add and scalar multiply matrices in a very simple way. Addition of matrices is merely component-wise. So to be clear, they have to be the same size. Otherwise, it's not defined. It doesn't make any sense. But if I have two matrices, like the one we have above, 1, 3, 2, 5, 7, 9, I like to read them in rows rather than in columns most of the time. Doesn't really matter. Plus 0, minus 2, 1, 4, 3, I don't know, 1 again. These, we just add them component-wise. So 1 and 0 makes 1, 3 and 2 make 1, 2 and 1 make 3. That's not how you write a 3. 3, 5 and 4 make 9, 7 and 3 make 10, 9 and 1 also make 10. That's how we add these things. And scalar multiplication just C times any matrix, which we could call fancy M, since I don't know what else to call it, just has whatever the ij entry is just, you take the ij entry of corresponding matrix M and multiply it by C. So to be more specific, if I want to multiply that matrix, here, we'll write the columns this time. I want to multiply this by -2. I just multiply every entry by -2. Kind of not much to it. Okay, and so with these definitions, we become convinced immediately that just like the space of linear maps is a perfectly good vector space, so is the space of matrices. And so we will call the collection of all matrices of size m by n will be denoted by f, and then rather than one exponent, we give it 2, fmn, for m by n matrices. If you go on the internet, you also see notation fm times n. Or of course, you can just see MN, but this last one is a little bit more suspicious because it's not obvious. Like, for example, if I just wrote F4, it's true that elements of F4 could be written like this, right? 4 entries. They could also be written like this, or they could be written, as rows, or maybe I just mean it in some other order like this, right? And so this last one is a little bit suspicious just because it doesn't really do much to clarify what the order is. But either of these two pieces of notation will specifically mean M by N matrices. All right, how long have we been talking? We've been going for 10 minutes now. So let's do just one last thing for this short video. And then next time we'll talk about we'll talk about what else you can do with matrices, what else they have to do with linear maps. But for now, let me just prove a little theorem. The dimension of fmn is equal to mn. And you might even ask, like, why is this like kind of not obvious? It is kind of obvious. And so the proof will be, I'll show you an explicit basis. The proof is we define Eij to be the matrix with a single one in slot ij. Every other entry is 0. And so I claim that this is a basis. To be a basis, you have to be linearly independent and you have to be spanning. And so, well, for linear independence, we can consider what would it mean if I did a double sum Aij, Eij, and I set that equal to 0. Well, this sum Aij, Eij would be the M by N matrix whose entries are the Aij, right? I don't really know how else to write this because I'm saying A11 times the matrix, which has a 1 in the top left corner, and then you have A12, which has its next entry, and then A13, and so on. This is that when you combine all those matrices, you add them up using the definition we just gave, that would be the big old matrix whose entries are Aij. Well, two matrices can be equal only when all of their individual entries are equal. And so, therefore, this implies that all the Aij are 0. So they're linearly independent. Why are they spanning? The proof for that is obvious. It's just look at it, right? If you give me any matrix, right, just a big old box full of numbers, of course, I can break this up into A11. Or how do I even write this? Like A11, E1. A11, E11 plus A12, E12. And so on and so forth. I forgot to write a lot of stuff. There, it looks good now. It's a correct sum. Intentionally written to look vaguely square to suggest this idea to you. Okay, I think this might be close to enough for one video. We've been coming up on 15 minutes now. I do want to suggest one exercise that's worth doing. I'm not going to make this homework, but in the spirit of a sort of warm up for the next video, when we're going to talk about matrix multiplication, check that if we have two linear maps, let's call them S and T in LVW, then we can talk about the matrix of S and the matrix of T. In order to go from here to here requires a choice of basis. Right? We were using the standard basis. I'm just going to write choice of basis. We're going to talk more about how much that choice matters and like what that choice does. But after picking a basis, the process we've been describing tells you how to go from S and T to M of S and M of T. My suggested exercise for you is to prove that this is well defined. In other words, for example, that S plus T in LVW, how about you check that M of S plus T is equal to M of S plus M of T. And similarly, that M of CT is equal to CM of T. This shows that once you've done this, you'll actually have proven that M is itself a linear map. What linear map is, what are the vector spaces? It's a linear map LVW to FMN. And, well, the stuff that I've been saying is very, very close to saying that this linear map is an isomorphism. But we haven't talked about isomorphisms yet. And so basically what I'm saying is if you think this through now, it'll save you some trouble down the line. And hopefully you will begin to feel like you understand the relationship between linear maps in the abstract and matrices in the concrete. All right, we'll stop here. And I will see you guys in the next one.